We will now see in detail how to build a random forest. We start by looking at the two main components of the forest, which are bagging, a procedure related to subsampling, and the randomization of splits within a decision tree. Let's start by recalling the construction of a decision tree. The algorithm of a decision tree takes as input a dataset and an impurity criterion. In each cell of the tree, the best cut is chosen. It is the one that maximizes the impurity reduction among all the cut direction J and according to all the cut positions S. This procedure is repeated for each cell until each leaf contains a single observation. A fully developed decision tree, i.e. containing only one observation per leaf, is thus created. As we have seen, such a tree overfits. It is therefore necessary to regularize it, i.e. to decrease its complexity, in order to improve its generalization performance. We then resort to a pruning step to obtain a smaller decision tree, i.e. a less deep and less complex tree. This prune tree is used for prediction. I invite you to go rewatch the session on decision trees if some of these steps are not clear. The procedure for building trees within random forest is the same, except that no pruning step is applied. The trees composing the random forest are therefore fully developed. Such trees have a low bias. The tree being very deep, it can approximate quite precisely complex regression functions. However, these trees have a large variance. Indeed, each cell contains a single observation, which does not allow precise estimation of the optimal value of the regression function in each cell. Such trees overfit and cannot be used as single estimators. Nevertheless, such trees within random forest are relevant because the aggregation operated by the forest will decrease the variance of the trees and thus produce a procedure with good generalization ability. Let's now look at the first ingredient used for the construction of a random forest, bagging. The term bagging comes from the contraction of bootstrap aggregating, the aggregation of several bootstrap procedures. Bagging consists of applying a learning procedure on several datasets, resulting from the subsampling of the initial dataset. This result can then be aggregated by taking their average or by computing a majority vote to obtain a more stable prediction. The subsampling step is performed by applying the bootstrap technique. More precisely, the bootstrap is a sampling scheme that consists in drawing n observations with replacement among the original n observations. By applying the bootstrap procedure, we obtain a new dataset, which is called the bootstrap or bootstrapped dataset. This bootstrap dataset can only contain the original observations. Some observations from the original sample are not present, and others are present multiple times. Let's introduce some notations. Starting from a dataset denoted dn, we create several bootstrap samples, which we denote d_1n for the first bootstrap sample, d_2n for the second sample, up to d_mn for the mth bootstrap sample. The integer m is a parameter of the procedure. We have m bootstrap samples at our disposal, all of which contain a part of the initial data with possible repetitions. We then apply a learning algorithm on each of these bootstrap datasets. This provides us with m predictions, which we can aggregate into a final output, calculating the average or majority vote. Let us summarize the bagging procedure. Starting from a single dataset, we construct several datasets on which we apply the same learning procedure. The results of these procedures are aggregated to provide the final output of the bagging algorithm. Bagging has multiple advantages. It improves the robustness of the model to a change in the initial data. Indeed, a change in data has less impact on the final predictor provided by the bagging, since the modified data will most probably not be found in all the bootstrap datasets. It will therefore have only a limited influence compared to the one it would have had if the whole dataset had been used instead of each bootstrap sample. Bagging is also a parallelizable method. The learning algorithm is applied separately to each of the datasets considered. We can therefore use a processor to train the learning algorithm on the first dataset, another processor for the second dataset, and so on. In practice, a processor will manage several bootstrap datasets. Finally, Bagging is a very generic procedure since it can be applied to any type of learning algorithms. Indeed, in this scheme, we have not specified the nature of the learning algorithm at all. I mentioned bagging to aggregate predictions, but we can also use bagging to estimate parameters of the linear model to produce a more stable estimate. In this session, we will only focus on bagging applied to decision trees. We will aggregate the predictions of each decision trees. However, there is a drawback to bagging. The individual predictors built on each of the Bootstrap datasets can be highly correlated. This is because all of these predictors are constructed from datasets resulting from the same initial dataset. The data from the Bootstrap datasets are quite similar, which can make the predictions of the trees quite close. The stability or variance reduction effect of bagging results from the averaging effect, and this effect is reduced when the different predictions are close to each other. We would therefore prefer to have individual estimators that are quite different from each other in order to improve the overall stability of the aggregation within the bagging procedure. Such a property is obtained via the second ingredient of random forests, the randomization of cuts.